Okay, this will be our first attempt to model both diffusion and reaction occurring at the same time, though we will be modeling them sort of separately. So I'll show you exactly what I mean. This is sort of a trick that you'll get used to. So suppose we have some sort of system that looks like this, where we have this catalytic surface over here at z equals 0, and we have a certain reaction as well, and the reaction looks like this. You have two species, A and B, with some stoichiometry reacting to C and D. But the catch is that the reaction only occurs at the catalyst surface. So if A and B are just hanging out in free space over here, they won't react. But if they make it over to the catalyst wall, then the reaction will occur and they'll generate C and D. Okay, to make things a little more simpler for us, just when we're starting out, let's actually define those stoichiometric coefficients and say that they're going to be these. So I arbitrarily selected these at random. We'll get back to that in a second. So to model the situation, let's think of it this way. Some time passes and we have some molecules that start moving toward the wall. So let's say that the red particles are A and the blue particles are B, and this is some time t in the system. At some later time, the reaction actually starts happening at the catalytic surface, and we generate some molecules of C and D. So this orangish over here is the generation of C, and this is a generation of D. So we start converting A and B at the catalytic surface to C and D, and then they start diffusing slowly away from the wall. So we have sort of another counter-diffusion example where A and B are moving toward the catalytic surface, and C and D are moving away from the catalytic surface. Okay, and then say even more time passes, and now our system looks like this. So now we have quite a large amount of A and B diffusing leftward toward the catalytic surface, and we have quite a bit of C and D, which is orange and green, moving away from the catalytic surface. So at this point now, it's time for us to try modeling the diffusion. At these points, at T1 and at T2, it's still too early, right? So our strategy is still to model this situation as some sort of steady state example. When there's no molecules, that's too early on. When there's only A and B, that's still too early on. When we just start getting C and D, that's closer. But when we have all the molecules existing now in some sort of system where A and B move left and C and D move right, now we're at a system that we can approximate with a steady state hypothesis and model as well. So we still need to be a little bit careful how we do it, and this is where the trickiness sort of comes in. So this purple box that I've now put into the diagram is what we are calling our control volume. Hopefully it's something you remember from Transport 1. Remember, whenever we needed to use the Reynolds transport theorem, we had to define what our control volume is. The control volume is essentially the system that we are going to be interested in. The trick here is that this control volume goes all the way out from infinity just up to the wall, but not including the wall. Again, that's pretty important. It goes right up to the wall, but it doesn't actually include the wall. What does that let us say? Well, if we zoom in really close, you'll see pretty much this wall here. You can imagine that's your catalyst surface. And then at a very small distance away, I guess I'll exaggerate even more, here's our control volume. So as you could see, our control volume does not actually touch the surface at all. The key here is that the box we've drawn, right, like I said before, you have molecules A and B, but they won't actually react in this space. They only react when they hit the wall. Similarly, C and D, they aren't going to interact with A and B in any way. None of the species in this purple box are going to react with each other. The only reaction that occurs is when they're right up against this catalytic surface, which means that when we are modeling diffusion within this purple box, within this control volume, we could say that there is no reaction actually occurring. In that regard, this is what I mean up here by saying we are modeling diffusion and reaction, but are we really modeling diffusion and reaction? Well, not exactly. We're modeling basically diffusion and reaction separately. The reaction happens over here. We ignore that pretty much, and we just look over here to the right where we have molecules moving back and forth. So we're modeling diffusion after the reaction has occurred. Okay, so that's the problem we're going to be looking at today. Later on, we'll actually model heterogeneous reactions or homogeneous reactions, and you'll see that they're a lot more difficult, especially heterogeneous reactions. You might actually need to take a kinetics class to do that. But for now, let's jump into our model where we have separated the heterogeneous reaction from the diffusion that takes place. So, as always, let's start with our diffusion convection equation. Alright, so I've already sort of noted here with the subscripts of C that I'm interested in studying the transport behavior of molecules C. I could have chose any of them, but in particular I'm interested in C. The assumptions we're going to make are the exact same assumptions we've been making so far, that it's steady states. That kills off this term over here. And the key point is that we could assume that there's no reaction. Again, is there a reaction occurring? Yes, it's happening at this catalyst surface, but that isn't part of our control volume. It is 1 nanometer away from it, and that's why we can say there's no reaction occurring in our control volume. And that's how we are able to model the problem in this way. So once again, we're going to assume it's a rectilinear geometry. So maybe I should be writing these in. So steady state, no reaction. And for the second one, we're going to assume it's one-dimensional, so it's only happening along the z direction, and it's Cartesian or rectilinear, whichever term you prefer. Now that we've made that assumption, we see the derivative of the total flux of C is going to be 0, which means that C is then a constant. At this point on, we are going to invoke the definition of total flux of C, and we're going to use the definition that includes the mole fraction of C as well as the total flux of all the species here. So that N is the total flux of everything. So if we expand that out, that's going to include the fluxes of each of the 4 components, A, B, C, and D. Even though we're interested in C, particles of C are still affected by the bulk flow of these guys, right? It's trying to move to the right, and it's going to be helped along there by the flux of C and the flux of D, but it's going to be hindered by the flux of A and the flux of B. And the way we actually represent that is sort of interesting. We take it directly from the stoichiometry of the problem, so I'm going to copy that down here. The stoichiometry of the reaction is going to tell us the relative amounts of molecules that are moving left and right in this problem. What it tells us is that the flux of A is going to be stoichiometrically related to C. It's going to be minus half of C, right? Why the minus sign? Well, remember A is moving to the left and C is moving to the right. So we have the minus sign because it's moving in the opposite direction. Same thing with B. B is going to be a reactant. It is also moving to the left, so it's going to be stoichiometrically related to the flux of C. And again, it's going to have that -2 out in front. And lastly, D, these green molecules are moving rightward. They're going to help carry along the molecules of C to the right, so it's going to be a positive flux. It's going to be stoichiometrically related as well, so that's why you have the 3 there. After you've done that, now you can substitute each of those values into your total flux equation for C, and then you have to do a little bit of algebra over here to just figure that out. So if you do the algebra, what you'll get is this result. And then this should be looking rather familiar to you. The next thing we are going to do is the same thing we always do, which is invoke Fick's first law, then combine Fick's first law with the total flux equation, and you'll see that you have a differential equation in terms of the mole fraction of C, as well as the coordinate system, which is dz in this case. So what we're going to do is we're going to do the exact same thing that we've done in the past when we got to this point. We're going to rearrange it so that we have the total flux of C on the left-hand side, and then we are going to separate variables. So distribute out that NC, so you have this term over here that contains the Y sub C term, and then you're going to separate variables. So these guys will be on the left. There should also be a dz over here. I don't know why that got dropped, but I'll copy it over. So this dz times that y sub c, and then this should be incredibly familiar to you. It's the exact same setup we had for the previous problem we did, which was the stagnant gas. So if you need some help solving this differential equation, go back to the stagnant gas video, modify it so that there's just 3 halves down there, and then follow the exact same steps. The only thing that might change a bit is the boundary conditions. So in the goal of modeling a more interesting problem, or at least a different problem this time, let's try to do the same problem with spherical coordinates. So say, instead of having a wall that all the molecules are moving forward, say there is a spherical catalyst surface, and those molecules A and B, which are again going to be, I believe, blue and red, are moving to the left, or I guess moving from anywhere in this space. I should copy this over, I guess. They're everywhere. Maybe, no, it doesn't even matter if I flip it. Rotate here, maybe. Let's try that. Hopefully you get the idea. They're coming from everywhere in space over to the sphere, and the molecules A and B are quickly reacting, and then they're moving away as molecules of C and D. So where that happens is at the point where R equals big R at the catalytic surface, which again, I've been careful to say that this control volume does not contain it. So again, we can make the same assumptions. And then farther and farther away, we're at R equals infinity. So essentially, we're going to be modeling the exact same problem as before, but we're going to be doing it in spherical coordinates, which you'll see complicates things a little bit in terms of the mathematics. What you'll see though, I guess, if you want to try this problem on your own, is we basically follow the exact same steps over and over again in our transport problems. I'll just leave that there. It's kind of bleeding into the diagram. So I'll move that over here. So we've been doing the exact same thing over and over again. First we draw a picture, then we use the diffusion convection equation, then we use the total flux equation, then we combine these two together, usually with the assumption that some relationship with the total flux is a constant. Then we combine it with fixed first law, we create constants, we do the indefinite integrals, we use the boundary conditions to solve the system and get the concentration profile. We return back to step 5 where we did the integral, we do it definite integral this time, we solve for the flux profile, and afterwards we can get the molar flow rate. So if that confuses you, I'm going to do exactly those steps here and you'll see what I mean. So the first thing we do in the problem that we're modeling is use the diffusion convection equation, which you should be getting used to by now. It's this guy, it's the exact same guy we used above. We're using the exact same assumptions we did in the previous problem. It's steady state, and there's no reaction that happens in the bulk because our control volume does not contain the catalytic surface. At this point here, we need to be careful that this del, because we're working in spherical coordinates, it's not going to be same del as in rectilinear coordinates. So here is the divergence you'll get for one-dimensional, spherical, one-dimensional in R, spherical coordinates. If you're confused about where this came from, go back to the previous lecture where we talked about modeling diffusion in cylindrical or spherical coordinates, and how this literally just comes from the formula that you'll find on Wikipedia for the divergence of some, I guess, quantity. Because we have that 0 over there, it makes it very easy to simplify. We're going to find out that the derivative of this equals 0, so whatever's in here is going to be a constant, which you'll find changes the problem slightly. Now we're on step 2 of our process. We use the total flux equation, again in terms of C. This is going to be the exact same process we did in the previous problem, because the stoichiometry is the same, so I'm going to skip ahead a little bit. We're going to get this result in there, and then we're going to do, once again, step 3 of our model, or our algorithm over here, is combine 1 and 2 by using fixed first law. So invoke fixed first law there, and then we're going to do the same thing we did in the previous problem. We are going to separate variables. So this should look exactly the same, that's why I'm going through it pretty fast. And then we get to this point. Again, we have this stuff over here and this stuff over here. I haven't yet moved the dr over, and that's because there's a little bit of a subtlety. In the previous problems, we've always been separating it so that the dz goes over here, and then we just integrate this side with respect to dz and this side with respect to whatever's left, the concentration, the mole fraction, but you need to be very careful. N sub c is not necessarily a constant if you're working in cylindrical or spherical coordinates under these assumptions. Why? Well, the result that we came up when we used the continuity equation was this. It was that r squared nc is a constant, not that nc is a constant with regards to r. So there is in fact a chance that n sub c, the total flux of c, is a function of r. So that makes it impossible for us at this point to separate the variables and put dr over there and put yc over here and integrate, because this could be a more complicated function. We don't know if this depends on, we don't know what this depends on, right? So we can't just integrate it or pull it out of the integral like we've been doing so far. But we do know that r squared nc is a constant, and that's the trick that we're going to use. So the trick is that we are going to multiply both sides of the equation by r squared. So now there's an r squared on the right hand side and an r squared on the left hand side. Then the next thing we're going to do is, now that we know that nc r squared is a constant, we know that the concentration we're going to hold relatively constant and the diffusivity is going to be constant. We're going to say, let's call that k naught and ignore it for a little bit. Remember, in our algorithm, we're at this point here, we're at create constants and do an indefinite integral. So we've just created a constant of all the stuff that isn't going to matter until later in the problem. So now we have that a constant is equal to all of this mess. And now what we could do, because that's a constant, is we could move the dr over to the left-hand side with the 1 over r squared and keep the rest of the stuff over here on the right-hand side. The other thing I want to do is I want to make the problem a little bit more general and say that, okay, let's forget about this 3/2 for the rest of the problem and just call it m, so that if the stoichiometry is going to be different, you could just say that it's going to be m and you're going to be modeling a more general case of the problem. So at this point, we are going to do the indefinite integral. So take the indefinite integral of both sides, and this is going to be a little mathy at this point, which gets a lot less interesting. So the indefinite integral of this 1 over r squared is going to be negative 1 over r, and over here on the right hand side, if you remember the integral of this form, if you use substitution, you're going to get the natural log of whatever's down here divided by this constant m over here. And if we rearrange that a little bit, we're going to get it like this. The reason I put this k prime over here is I've moved the negative sign from this term and I've absorbed it into that constant there, which is again something we do a lot when we're modeling these problems. So now we're at step 6 of our algorithm. We need to formulate the boundary conditions. So this kind of got chopped off over here, but this end over here was at r equals infinity, the end of this control volume. And our two boundary conditions are going to be this. When you're at the catalytic surface, you're going to have some mole fraction of C. We're just going to say that's some value. We don't know if it's 1, we don't know if it's 0.8, we don't know if it's 0.7. It could be any of those values. We're just going to leave it at that. But when r equals infinity, we're going to say there's almost no product over there. Why? Because remember, the product C is going to be generated at the catalytic surface. We're going to say it's pretty much never going to get all the way out to infinity. So we can say the mole fraction of C at that point is going to be pretty close to 0. So using those boundary conditions, we're going to find out what these constants are approximately equal to. So the first thing I'm going to do is I'm going to use the second boundary condition. What that does is that this will become 0, so the ln of 1 will be 0. Over here, as we take the limit of this goes to infinity, that's also going to be 0, so what we get is that k1 is going to be 0, which simplifies our problem slightly. The next thing we're going to do is we're going to use the other boundary condition to get k0 prime. So this is what we have left. When we use the second boundary condition, what we get is this. Perhaps I skipped ahead a little bit. Let's see if I could clean that up a bit. Alright, so the intermediate step is over here. If we're at big R, then I'm just going to move this big R up over here, and I'm just going to say this is y sub c s. And then we're going to go back to here, plug that in, and we should get this. Again, the mathematics isn't too interesting. You could do that on your own time and see exactly the nitty-gritty of what's going on there. So we have ln's on both sides. We're going to remove those ln's, and we're going to get this. And then lastly, if you simplify a little bit, this is going to be your final concentration profile for the mole fraction of C in a spherical system where we're modeling diffusion and reaction separately. Okay, now we're at, I believe, maybe step 7 or so, maybe even step 8. We're at step 8. Return back to 5 and do the definite integral so that we could get the flux profile. So returning back to the point where we had that initial constant k naught, we have this going on. And now we need to do the definite integral. Again, this is a constant, so I'm leaving it out of the integral. Our definite integral goes from r to infinity, and the known mole fraction at the catalytic surface out to 0. So it's pretty much the exact same thing we did before. When you do the mathematics, what you're going to get is this. Again, it's not too interesting, so I'm just going to sort of speed through it so you can see the final result. But this right here will cancel out, which is why we use that boundary condition. And over here, this will cancel out as well, so you're just going to get these terms remaining. Now that that's all that's left, you could solve for n sub c, and when you actually see it, it is a function of r, which is something we haven't seen before. Up till now, we've always seen that the total flux is going to be constant, but this time it is not. It is actually dependent upon the coordinate system. It's dependent upon r. So we're almost done here. There is something that is constant though, right? So we've found the total flux profile, but we don't yet know the molar flow rate or the transport rate that we call F. So the molar flow rate, because of the units, remember flux is in moles per area time. The molar flow rate is in moles per time, so if you take the flux times the area, you'll get the molar flow rate. Well, if you remember back to this point, remember that r squared times n sub c was a constant, right? So I've just moved this r squared back to the left-hand side. And you also know that if this is a, I guess, spherical system, then the thin film that we might be describing is going to be with the surface area of that sphere. So it's going to look like 4 pi r squared. If you're a little bit confused about that, go back to the cylindrical and spherical diffusion video. But knowing that it's going to be the surface area, knowing it's going to be 4 pi r squared, we can multiply both sides by 4 pi. And what we get is that the molar flow rate of the system, the transport rate, is going to be equal to this. Which is pretty remarkable, right? Because if you notice in here, 4 is a constant, pi is a constant, diffusivity is a constant, the concentration we're assuming is relatively constant, the radius of the sphere is constant, m is given by the stoichiometry, and the mole fraction of C at the catalytic surface is constant. So everything here is constant. Don't be afraid that this is negative, because it's going to be 1 minus some number, so it's going to be a decimal. The ln of a decimal is going to give you a negative number, so these negatives will cancel out and you'll get a positive number. But what I'm trying to get at is that all of these are constants. What you see is that, well, the total flux of C is not constant, since r squared times the total flux of C is constant, the molar flow rate or the transport rate to the system will be constant. So the takeaway isn't exactly the concentration profile with the total flux profile, or even the molar flow rate of this particular problem. It's the algorithm you use to generally solve these. If you go through these steps, if you think about the assumptions you make, if you carefully replicate this every single time, as long as you model the problem correctly, as long as you get that initial setup, you